to mathematical modeling by Lauren, Chelsea, and Landon. So here's the problem. Jill's dad is wanting to turn their basement into an indoor fitness room. The architect Steve has left them with the general information about the room, and now they must answer the following math problem to help them figure out the best way to accurately maximize the new space. Problem is, neither one of them know how to solve it, so they're calling you for help. So, the plan for the indoor fitness room consists of a rectangular region with a semicircle on each end. The perimeter of this running track is 200 meters. So first, we must write a function that models the area of the fitness room as a function of the radius r of the semicircles. Second, for what values of the radius will the area of the fitness room be at least 3,000 meters squared? And third, if the gym wants the area of the semicircles combined to equal the area of the rectangle, what radius will they need to use? So, it's important to list all the equations that might be helpful. What do we know? The perimeter of the room is 200 meters. Formulas that may be helpful are the area of the circle, which is pi r squared, since there are two semicircles which equal one whole circle. We also need the perimeter of these circles, which is 2 pi r. We will also additionally need the area of the rectangle, which is x times y, or length times width. And then the perimeter of the rectangle, which is 2x plus 2y.
Step 1. We will start off by drawing a rectangle with a semicircle on each side. Then label the sides that have the semicircle x and the other two sides y. We will then note that the perimeter is 200 meters. After the shape is drawn, we will change each x into two r's, each representing radius. We do this because x is equal to the diameter and the radius is half of the diameter. This will make solving the equation much easier overall. Now, to start solving the equation, we must find the independent variable and the dependent variable. An independent variable is a variable that does not depend on another number or variable to get its number. And the independent variable of the equation is radius. And the dependent variable is the variable that will change according to another variable, which is area in our equation. Now, the first part of the equation asks us to find a function that models area in terms of radius. To do this, we will find y in order to complete the equation. We will start out with the equation of 2x plus y is equal to the perimeter. Then, because we know the perimeter is divided by 200, we will replace the perimeter in the equation with 200, and we will replace the x with pi r. Then, in order to get y alone, we will subtract 2 pi r to the other side of the equation, then divide everything by 2 in order to get rid of the number 2 next to the y. After that, we will get y equals 100 meters minus pi r, which is the final answer, which we will put into the equation.
Now, to answer question number 1, we must put together a function where area, the dependent variable, is in terms of r, the independent variable. Since we know the area of a circle is pi r squared and the area of a rectangle is length times width, or in this case, x times y, we must combine these two equations together. So, the base equation would be a in terms of r equals pi r squared, the area of a circle, plus x times y, the area of the rectangle. Now that we know the area of the rectangle is x times y and the variable x is equal to 2r, we rename x in the equation with 2r. So our equation is a in terms of r equals pi r squared plus 2r times y. Once again, now that we've already solved for y in the previous slide and found that y equals 100m minus pi r, we can rename y in the a in terms of r equation as a in terms of r equals pi r squared plus 2r times 100m minus pi r. Finally, to convert the a in terms of r equation into simplest terms, we must distribute 2r into 100m minus pi r, making the final equation a in terms of r equals pi r squared plus 200r minus 2 pi r squared. Question number 2 asked what the specific radius values are when the function a in terms of r is greater than or equal to 3,000 meters squared. To calculate these values, we type the a in terms of r equation into a graphing calculator as y1 and set y2 equal to 3,000 so we could see where the graphs intersect. The two radius values that allowed the a in terms of r function to be greater than or equal to 3,000 meters squared were 24.2 and 39.5. So, to write these values in the correct format, we wrote our set notation to show that the a in terms of r function is greater than or equal to 3,000 meters squared when r is greater than or equal to 24.2 and when r is less than 39.5. Anywhere between these two values for r is when the a in terms of r equation is equal to or greater than 3,000 meters squared. Finally, in question 3, the problem asks us to find the radius where the area of the semicircles combined equals the area of the rectangle. So, going back to the a in terms of r equation, we know that pi r squared is the area equation of the two semicircles combined. Since the problem asks us to find the radius that would make the area of the semicircles equal to the area of the rectangle, we set the area of the semicircles combined equal to the area of the rectangle. In doing so, we get the equation pi r squared equals 200r minus 2 pi r squared. Next, we must put pi r squared into y1 of our graphing calculator and 200r minus 2 pi r squared into y2. Now we press graph and find the point of intersection. The point of intersection turns out to be 21.22 1414.71. We use the x-coordinate to determine our radius value that will make the area of both semicircles combined equal the area of the rectangle, which turns out to be 21.22. To recap, in number 1, we found the function that models the problem as a in terms of r equals pi r squared plus 200r minus 2 pi r squared by taking the base equation of the shape a in terms of r equals pi r squared plus x times y, and solving for x and y and inserting the outcome of those variables into the a in terms of r equation, which then became a in terms of r equals pi r squared plus 200r minus 2 pi r squared. To answer question 2, we inserted the a in terms of r equation into our graphing calculator in y1 and then inserted 3,000 into y2 and look for when the graph and line intersect, to find 2 points where the x or r value would make the function be more than 3,000 meters squared. The two r values were 24.2 and 39.5. And lastly, to answer question number 3, we entered the area equation of both semicircles combined and the area of the rectangle to find the intersection between the two. We then took the x-coordinate or r value of the coordinate, which told us that when r equals 21.22, the area of the semicircle and rectangle equal each other. And you are done. Thank you for helping Jill and Steve.